Yes, good morning. And this is P. Shivashankar Rajamani, Associate Professor, Department of ECE, KSR College of Engineering. Today, we are going to see about mesh current analysis using Cramer's rule. Many of them have used the equation to solve the mesh analysis. Here we are going to use Cramer's rule in order to save time. So the procedure for solving this Cramer's rule is, if you want to know the R11, that is the total resistance in the first loop, right? So for my consideration, I have took three loops: first loop, second loop, and third loop, right? So R11 represents the total resistance in the first loop. You just add all the resistance in the first loop. Then R12 represents the common element or common resistance between the first loop and second loop. Right. Sometimes you will be putting minus if the current direction of your first loop and second loop are in opposite direction. If it is in the same direction, you will be putting positive. Then R13 is the common resistance between first loop and third loop. If there is a common resistance, you will be using the resistance value. If there is no common resistance between first loop and third loop, you will put it as 0. Then R21 is the common resistance between second loop and first loop. The R12 and R21 will be the same. Then R22 is the total resistance in the second loop. We have to add all the resistance in the second loop. Then R23 is the common resistance between second loop and third loop. Same, if the direction of your second loop and third loop are in opposite direction, you will put minus. If they are in same direction, you will be putting positive. Likewise, R31 is the resistance between third loop and first loop, which is very similar to your R13. Likewise, R32 is the common resistance between third loop and second loop, which is very similar to the R23. Then R33 is the total resistance between third loop. So you have to have the total resistance in the third loop. So this is the equation. So R11 is the loop between first loop and second loop. R12 is the, if the current direction is 1 and 2 are in opposite direction, we will put minus. Likewise, first loop and third loop, if it is in current direction in the opposite direction, we will be putting minus. So R13 and R21 will be the same. Likewise, R31 and 13 will be the same. Likewise, R23 and 32 will be the same. So only the diagonal elements will be in the value. So we have this equation, Ohm's law, V is equal to I into R. So I is the total current which is flowing in the loop 1, I2 is the current flowing in the loop 2, and I3 is the current flowing in loop 3. So this is the thing that we have to find, and V1 represents the voltage in first loop. If there is a voltage, we just see whether it is moving from negative to positive. If it is like that, we put it as positive. If it is moving from positive to negative, put it as minus. For finding the value of I1, so replace the first column by V1, V2, V3, and the remaining things will be the same. Divided by the whole del, where del will be the normal matrix R11, R12, R13, right? So it will be very equal for all the values. Likewise, in order to find your current in second loop, your second column has to be replaced by the voltage source, whereas the bottom will be the same determinant value, will be the same. Likewise, in order to find your current I3, you have to replace your third column with voltage source, that is V1, V2, V3. We will go for a problem. Right. Using mesh analysis, calculate the current in all the loops and also calculate the power dissipated by 250 ohm resistor. So we will find the current and we will compare with the normal equation method also. So I took 100 ohm and 300 ohm as my first loop. and 300, 250 and 50 as my second loop, and 100, 250, 150 as my third loop. So this is my assumption of my current direction. So I have took all directions are in clockwise direction. So if you want to substitute your R11, so just look into that. So just add all the resistance in loop 1. So in loop 1 we could able to see that 300 plus 100, so it is 400. Likewise for R12, so it is the common element between your first loop and second loop. So first loop and second loop, the common element is 300. So since the current direction of your I1 and I2 are in opposite direction, it has been put it as minus 300. And likewise for R13, which is the common element between your first loop and third loop, since the current direction is opposite, so I have put it as minus 100. So likewise R22, so if you add all of your resistance in second loop, so 300 plus 50 plus 250, so it is total R22 is 600. So I have replaced by 600. Then 250 is the common element between your second loop and third loop. Since the current direction of your I2 and I3 are in opposite direction, I have put it as minus. So you might be having one question. So what happens if the current direction is same? You just put it as positive. If both the current I2 and I3 are in same direction, put it as positive. So this is the matrix. So we need to find the I1, I2, I3. So we will see the voltage. So we have only voltage source in the first loop alone. We don't have any voltage source in second loop and third loop. So your voltage source will be 0. In your first loop, since the current assumption is from negative to positive, so I put it as 50 plus 50 voltage. So first we need to find the determinant of the matrix. So if you find the determinant, so it was 29 followed by 6 zeros. So in order to find the current at loop 1, so just replace your first column with the voltage source. Remaining procedure will be the same. So I have used a calculator to solve this. So I have already done this calculation in the calculator. So I have find the determinant. So I have to use 7. So it is shift 4. So it's so I put it in matrix A, so my value will be 3. So if you just equate it, so I will be getting the same answer. It is 11, 87, 5000, right, which is very similar using the calculator. So if you divide by this by 29 followed by 6 zeros, so I will be getting is my current value will be my current is 0.4095, which is approximately 0.410, right? Likewise, we need to find the current at second loop. So replace the second column with the voltage source. So if you find that your current is, it will be very similar. So I will use this calculator to use this to find my second matrix. So you just shift with 4. So I need to find the determinant. So I already saved this value. So I just keep on typing the thing. So it is, my data is in 4, which is B. So which is equal to, so I am getting, it is 875 followed by 4 zeros. It is divided by 29 followed by 6 zeros. So I will be getting the current. It's 0.0317. So it's approximately 0.302. Right. So we'll go for to find the current at loop 3. So replace the resistance in column number 3 with the voltage source. Then do the same procedure. So we could able to see that I have saved this value in my calculator. So I'll just use this calculator to solve this. So determinant. So we have to find the determinant. So use this. So I have saved my data in C, which is 5. So it is 675 followed by 4 zeros. Right. So it is divided by your determinant. So determinant is 29 followed by 6 zeros. So I will be getting the current value. So it's 0.2327, which is approximately 0.233. So my current is I1 is equal to 0.410, which is approximately approximated value. So I2 is equal to 0.302. Likewise, I3 is equal to 0.233. Now we will use this proof with the equation. So in the first loop, we already know that voltage sources, we use Kirchhoff's voltage law. So sum of potential rise is equal to potential drop. So potential rises, it's 50 voltage, which is equal to all your potential drops. So it is 100 into I1 minus I3 plus 300 into I2 minus I1. Right, so if you simplify this, so you will be getting 50 is equal to 50.1. There is a small error. This error is because of calculations error. So it is very similar. Alright, so in your loop 2, so we don't have any voltage source in the second loop. So it is, we use the same KVL equation. So potential rise is 0. So potential drop is, it's 300 into I2 minus I1 plus 250 into I2 minus I3 plus 50 into I2. So if you simplify this, so you will be getting, again you have a small error, it's 0.05 you are getting. So it is 181.25 minus 181.2. So there is a small error because of its round up error. Likewise, if you see the current in the loop 3, so here also you could be able to see that the voltage source is 0, that is potential rise is 0. So you will use the equation. So it's 100 into I3 minus I1 plus 250 into I3 minus I2 plus 150 into I3. So if you simplify this, you will be getting minus 17.7 minus 17.25 plus 34.95. So it's approximately is equal to 0. So in the using the Cramer's rule also we could be able to see that 0 is equal to 100 into substitute the value of your I1 plus 250 into substitute the value of your I2 plus substitute the value of your I3. Here also we have the equation, total is 0. So we have proved that same, the answer for the Cramer's rule on the equation rule are same. The only advantage is Cramer's rule saves the time. The question is asked is, what is the current